Hey guys, in this video I'm gonna show you something about compact sets. So just like closed and open sets, compact set is something is another character to describe a set. And with compactness, there are actually a lot of compactness is such a good property or good character for a set, because with the compactness you can somehow have a smoother or easier way to get to the result of some theorems, and it actually provides some famous theorems a very good condition. Okay, so now let's just get started. Before we formally introduce the definition of compactness, we will first introduce you the open cover. So what is open cover? Because it will appear in the definition of compactness. So what is open cover? We call a collection G alpha of open subsets of X an open cover of V if it is contained in the union of G alpha. So now we are firstly given a metric space X, and E is the the subset of X. And what is the open cover V? So first of all, you will have a collection of open subsets. So that is what we call it open cover. The subsets have to be open, and also since it calls cover, so the collection will cover the subset E, right? So it is contained in the union of the collection of, the union of all the subsets. Okay, so that's a very straightforward definition, because open cover mainly focus on open and cover. That means the subsets that cover the subsets that cover the set E should all be open. Okay. So now let's move on to the definition of compactness. So now we are given a metric space X and a subset K of a metric space X. And when will we call it compact? If every open cover of K contains a finite subcover. So what does that mean? It means well, for a subcover of X, you can have a lot of collection of open subsets, right? As long as it covers the subset K. But to be compact, you must contain every open cover, no matter what kind of open cover you choose, you must contain a finite subcover. So there must be a collection which contains finitely many subsets, and this collection that contains finitely many subsets must cover E. Must cover K. Okay. So here I said that is to say, if G alpha is an open cover of K, and then there must exist finitely many indices alpha 1, alpha 2 to alpha n, and such that K is contained in this kind of open subsets. Okay, so for example, if we take sets like this, okay, so if the set is like this, so x larger than 0 and y larger than 0, or larger or equal to 0, this set cannot be compact, right? Because well, here you will go infinitely large, or infinitely farther, and you cannot take finitely many subcover that can contain the set, right? So previously we said subcover or open subsets, we can somehow define it. We can somehow say it as the circles. So to find the to find finitely many subcovers, it's like find finitely many central points, right? Central points with radius. But the radius itself has to be real numbers or finite, right? So if a set is something like this, x larger than 0 and y larger than 0, you cannot find such kind of finitely many points, right? Finitely many central points, because no matter what kind of points you find, there will always be some points lies farther than the farthest central point you choose, right? I mean, the farthest central point with its neighborhood, I mean the circle, right? Okay. So now there is a remark, that is to say, every finite set is compact, right? Because, well, it is finite, so definitely we can find a finitely many subcover, right? Okay, it's pretty simple. And now let's move on to another theorem. It says, well, suppose now we have k is contained in y and y is contained in x. This theorem is pretty much similar to the one we previously talked about, the relative open, right? But in the previous case, we can only say that if y is contained in x, k is contained in y. If k is open in x, we can say that k is also open, so relatively open in y, right? But conversely, it might not be true. But in the compact case, it is true. If k is compact relative to x, if and only if k is compact relative to y. So it's like k is compact in y is equivalent to k is compact in x. Okay. I'll show you the proof of it. So now we assume that, first of all, k is compact relatively to x. Okay. We're gonna show that k is also compact in y. So we're gonna show that for every open cover of y, open cover of k, we can find a finite subcover, right? And now we just let V alpha be the collection of subsets that open relative to y, such that k is contained in the union of y. Okay. Well, k is the subset of y, so this can happen, right? We can find collection of sets that open relative to y, and k is contained in the union of y, right? Y alpha. I'm sorry. I think I should write V alpha. I'm sorry, V alpha. Okay. So also we know that there are sets G alpha open relatively to X, right? Such that V alpha is the intersection of Y and G alpha, right? Because, well, Y is contained in X, right? And now we wanna find V alpha, which is open in Y. How are we gonna find it? If we can find some, open set in X, and the open set V is just the intersection between Y and this open set G. And it can happen, and it will always happen actually, because actually we have a theorem. I think I didn't mention it in last video, but we'll just quickly say it. So the theorem says that suppose now y is a subset of x, and a subset of v of y is open relatively to y if and only if is equal to y intersects g for some open subset g of x. Right? So now we are given like x like this and y like this. A subset of y. So E here is E is open relative to y if and only if E can be some sets E can be y intersects some set G that is open in X, right? So here in this case we can just take G to be E, right? So y intersects like G. Well, G is certainly open relative in X. I'm sorry. So we just take G here, and y intersect G is G itself, right? And we call it E. We just define E like this. So we now find E, right? So I'm not gonna prove this theorem. I don't think it's difficult to prove that, but we are still gonna focus on compact sets for this video. Okay. So that being said, we can always find such kind of G alpha, right? For any alpha. Okay. So now since K is compact, right? K is compact relatively to X. So we have a finite subcover, right? So K is contained in G alpha, the union of G alpha 1 to G alpha n, right? And we know that alpha 1 to alpha n is finite, right? Since K is compact. So now we also, since K is a subset of Y, K is also contained like in the union of V alpha 1, the union of V alpha, right? V alpha 1 to V alpha n, right? Because and just think about how did we get like V alpha? V alpha is just the intersects of G alpha and Y, right? And now G alpha is infinitely many. G alpha is now G alpha is finitely many. It should say G alpha 1 to G alpha n is finitely many. And for each alpha I, we can take the intersection of Y and G alpha I to get V alpha I, right? So we will get finitely many V alpha I, and K is contained in such kind of union of V alpha I, right? Okay. So now we find that K is compact relatively to Y, right? Okay, so now conversely, here now we assume that K is compact relatively to Y, and we want to show that K is also compact relative to X. So let's first take a collection of open subsets of X, G alpha, which covers K. And now we take V alpha, and V alpha is generated by the intersection of Y and HG alpha, right? And now we know that R is compact relatively to Y, so K is compact relative to Y. So K is contained in a finite subcover of V alpha, right? So we get V alpha 1 to the union of V alpha 1 to V alpha n, and K is contained in that union. And alpha 1 to alpha n is finitely many, right? And also, just think about how we get V alpha. V alpha is the intersection of Y and G alpha, right? So that said, every V alpha is contained in G alpha, right? So since K is contained in the union of V alpha, we also know that K is contained in the union of G alpha I to G alpha, the union of G alpha I to G alpha n, which is also a finite subcover of X, a finite subcover of K, right? So now we get the point that K is compact relatively to X, right? Okay. So, well, as I said before, compactness is another like important character for a set. In fact, we can somehow like connect the open and close. I'm sorry. We can somehow like connect. There is some like connection between the characters of a set. So we say actually, a set is compact if and only if it's closed and bounded. So this theorem you can also use it to prove that some set is compact if you can prove it's closed and bounded. And also, if you are given a compact set, you will have the properties that the set is also closed and bounded, right? And I think bounded is very straightforward because if a set is compact, it means it has like a finite subcover that can cover the set, right? And since it's finite, you can always find some like larger circle that large enough to contain all the points of the set, right? Okay, so basically it's bounded, but how we gonna prove it's closed? It's not that difficult. I mean, so I'm not gonna like rigorously write down the proof, but I will provide you some ideas on how to prove that a compact set is closed. So this is actually another theorem. Compact subsets of metric spaces are closed. Okay, now let's just assume that we have a metric space X and K is a subset of that metric space, and now K is compact. And we want to show that K is closed. But in this case, we want to like show K is closed by proving that the complement is open. Okay. Remember in the videos for open and closed sets, we said that a set is open if its complement is closed, and a set is closed if its complement is open, right? And those theorems or results that are valid on real line can also be expanded on, can also be like generalized on the Rn space. Okay, so for metric space, it's still valid. A set is closed if its complement is open. So how are we gonna prove the complement of C is open? Say we already say here we have a set X, right? Here's a set X, and suppose K is something like that. K is here, and now K is compact. We want to show that the complement, which means here, is open, right? So to show the complement of C complement of K is open, is equivalent to show that every point in it is interior point, right? So if we like take arbitrarily a point P, we want to show it's an interior point. So how to show it's an interior point? Interior point is where you can take a there exists some like neighborhood of it, such that the neighborhood is purely contained in the set, the complement of K, right? Okay. So I think that's not a problem to show that, because, well, suppose like we if we arbitrarily take a point P in the complement, then next step we just take Q. So like if we have another point Q which is contained in K, then we let VQ and WQ represents the neighborhoods of P and Q. Neighborhoods of P and neighborhoods of Q. And here the neighborhood, I'm not saying the neighborhoods is one neighborhood. I mean it represents all neighborhoods. It can represent all neighborhoods, right? And also for every neighborhood, the radius we take the radius of each neighborhood such that the radius is like smaller than the half of the distance of PQ. Okay. So now we are given that K is compact, right? So that is to say, K is contained in finitely many like subcovers, right? So there are finitely many points Q, such Q like this, Q1 to Qn, such that K is compact in the neighborhood of these central points, right? Q1 union to WQN, right? Okay. And also for the point P, we can get so we want to prove its interior point. So we want to find a kind of neighborhood that satisfy the condition, satisfy that the neighborhood is purely contained in the complement of K. So how are we gonna find that neighborhood? We just take okay, if we let V be the ideal neighborhood. Okay, so V is, if you take the intersection of Q1, Q2 intersect Qn until Qn. Okay. And this is how we're gonna get the neighborhood of P. And you know that P does not intersect with W, right? I'm sorry, I should say W is the union of all the neighborhoods that we take. And here here the like subscripts, I use Q1 to Qn just to did you know that it's finitely many? It's finitely many, but for every VQI, it's still the neighborhood of P. Okay. Okay, so well, since every neighborhood has radius smaller than half of the distance of PQ, so the intersection of V and Q will not will be empty, right? Because they don't have overlapping part, right? So that's how we so V intersects W will be empty. That is to say, V is contained in K's the complement of K, right? Because K is contained in W, and V has no intersection with V intersect with W is empty, so V is wholly totally contained in the complement of K, right? So P is the interior point, right? Since P is arbitrarily chosen, we now prove that the complement of K is open, so K is closed, right? So we prove that a compact set is closed. Okay, the last theorem I want to mention in this video is that, okay, now we have a compact set K, and it is the subset of K, and it is infinite. So the condition points out so the theorem points out two conditions. One is a compact set K, and the second one is a subset is infinite. E is infinite, and the result will be E has a limit point in K. So for this theorem, we will prove it by contradiction. Okay, because it says E will have a limit point, right? So the contradictory statement will be like E will have no accumulation point or limit point in K, right? Okay. So what we will get if we suppose E has no accumulation point in K? Well, suppose we have if we take any point in K, like for example Q, we take we take any point Q in K, then the neighborhood of Q, VQ, we call it VQ, will contain at most one element of V. Just think about this statement. If E has no accumulation point in K, then for each point in K, the neighborhood of that point will contain at most one element of V. And if the point that we take is contained in E, is a point in E, then the element will be itself Q. And if the point Q that we choose is not contained in E, then there will be no element. The neighborhood of Q will contain no element of V, right? Because just think about it. If you have elements other than Q, then what will happen? Then the neighborhood of Q contains some points in E. That said, the intersection of the neighborhood of Q and E is not empty, right? So Q will be a limit point of K. But Q will be a limit point of E. But we suppose E has no accumulation point in K, right? Because Q lies in K, right? So this is not gonna happen. Okay, so now I know that the neighborhood of Q will contain at most one element of K. The neighborhood can be any neighborhood of Q, right? For every neighborhood of Q, the elements in the neighborhood that lies in E will be at most one. So that is to say, we will not have a finite subcollection of VQ, neighborhood of Q, that can cover E, right? Because for every neighborhood, you can only for every neighborhood of Q, you either contain only one element or no element. So if you take finitely many, you cannot get infinitely many elements of E, right? Because E itself is infinite, right? So, well, since VQ cannot cover E, VQ cannot cover K as well, right? Because E is contained in K, right? As said. So, well, as you know, K is compact. Compact means for every cover of a K, every collection of subsets that cover K, you will always find some finite subcover that also covers K, right? But now the collection of neighborhood of Q, you cannot find finite subcollection of VQ, right? So under such case, under such condition, K is not compact, which is contradictory to the condition of the theorem. So that's the same to say that E has to have a limit point in K, right? So that's basically how we're gonna prove the theorem. So that's the video for compactness, but actually there are a lot of other theorems and concepts in the book. I'm sorry, I did mention that all the theorems and definitions that I'm using here and the proof are basically from the book Principles of Mathematical Analysis. I remember I've already mentioned it in the previous videos, but I will also put the book information in the information bar. If you like, you can go and check. And there are a lot of theorems, and some of them I think it's very like obvious, and I just picked some of the theorems to show you in these videos. But if you're interested in it, you can go and check that book. There are a lot more, much more than the theorems that I present you here. Maybe I'll do another video about compactness sometime. Okay, so that's it. I hope you like it. You may leave me comments or send me emails if you have any questions. Hope you like it, and bye bye. See you in next one.